Reason why we call this a normal distribution, because it occurs a lot in nature. I'll give you an example. The first problem that we encounter on that PDF file, if I take a look at it, says, assume that the average height of adult Caucasian men has a mean of 68 inches, that's 5 foot 8 inches, and a standard deviation of 4 inches. Spread of 4 inches, a middle of 68 inches. Well, our expectation is that if that's the average size for men, 68 inches, that we're going to get half of the men are going to be less than that, and half of the men are going to be taller than that, right? The other thing that we think of intuitively is that's an average height. That means a lot of people are going to be around that height. So there's going to be a lot of people that are 68 inches, not everybody, but a lot. But there's also going to be a lot of people that are 67 inches, 69 inches, 66 inches, and so on and so forth. And we also say to ourselves intuitively that as we get further and further away from that average, we're going to find fewer and fewer people that are represented within that group. There's going to be very few Caucasian men that are under 5 feet tall, under 60 inches. Very few that are over 73 inches. I think the tallest player in the NBA right now is 73 inches, right? No, he's taller than that, right? 6 foot, I mean, 60, no, that's about right. 74, whatever. I was just watching The Princess Bride, right? We know somebody in there that's 74 inches tall, right? Right? Andre the Giant, right? So at any rate, but that's a rarity. I mean, literally people called him a giant because he was so large, right? So we know as we further and further away that we get from the mean, we know just naturally we're going to get fewer and fewer occurrences. And that's what this normal distribution represents. It's really based on chance. In other words, if half the people are over 68 inches, half people are under 68 inches, and you start populating this with people at random, you're going to start to populate the middle of it more and fewer people on the outside. And you'll build up kind of like you build up a histogram. And this is kind of like the ultimate histogram. It's an entire population or a mathematical representation for a perfect population. Again, based on probability theory. That's why we went through this whole process of learning a little bit about probability to start off with. But the really important part is that these normal distributions, since they're all based on the same assumptions about the way probability works, they're all going to have certain properties in common, properties that we're going to be able to take advantage of to use as a tool. So for instance, whether they are very tall and narrow, or whether they're average width and height, as this one is, or let me just get back here. I have one on this sheet also, or whether they are really tall and narrow, or whether they are squat and wide. If they're a normal distribution, right? If their distribution is due to chance and they're normally distributed, the means in the middle and the medians in the middle and so on and so forth, they're going to have a property that's in common. And that property is that the distribution of the occurrences is going to be such that 68% of, in this case, Caucasian men are going to be between one standard deviation below the mean and one standard deviation above the mean. Okay, and it doesn't matter whether you're dealing with this distribution or you're dealing with this tall, narrow distribution, right? In any case, whichever distribution you're dealing with, you're always going to have 68% of the distribution. This is roughly 68% of the distribution between one standard deviation above the mean and one standard deviation below the mean. Okay. Now you might also notice here that we have another range here, 95%. 95% of the population is going to be between two standard deviations below the mean and two standard deviations above the mean. Okay. I'm using the Greek letter sigma to represent standard deviation. Okay, when I write sigma, am I referring to the population standard deviation or a sample standard deviation? Is there a way to know? Anytime I use a Greek letter like mu for mean or sigma for standard deviation, I'm referring to the population standard deviation and the population mean. If I use X bar or S, I'm referring to the sample standard deviation or mean. Okay, so for the time being, we're going to use that to kind of differentiate. Most of what we're going to be talking about tonight, we're going to be assuming we know the entire population. Next week, and then subsequent, well, not next week because we have a nice test next week, but in subsequent weeks, we're going to be applying this to samples, and things change a little bit when we apply it to samples. Okay, but they change in a good way. They give us another tool that allows us to make predictions about the population from samples from this same kind of tool. Okay, so at any rate, we're dealing with population now. How about 3 standard deviation below and above? What is it? You guys are looking at the same graph I am, right? 99.7. Almost everybody is within that range of 3 standard deviations above and 3 standard deviations below. Okay, so we're going to apply this right now. This is a kind of a general rule. It's not very precise. It's not perfectly accurate, but it's good enough for us to make some general assumptions about a population. Okay, so let's take a look at what we have here. Okay, assume that the height of adult male Caucasians, 68, mean of 68 inches, standard deviation of 4 inches. What's the probability that a randomly chosen individual it has a height that's greater than 68 inches? The mean was 68 inches. What's the probability that a male in this population is going to have a height greater than 68? I don't even really have to look at the chart there, do I? Because it's the mean, what the probability is the same having higher and lower, probability is 50%, right? And if we look at this graph, right, well, that's this is the mean, right here, here's the mean, right? And probability of being above the mean is half of the area of that distribution. So what does that tell us? The area of that distribution represents the percentage of the population. This entire distribution represents 100% of the population. Half of it represents 50% of the population, and so on and so forth. So I can use this diagram kind of as a tool to help me with my calculations so I don't mix things up. Okay, so now I'm going to go into the next part. Probability that adult Caucasian men have a mean with a mean of 68 inches, have a height between 64 and 72 inches. I'm going to go on here, and I'm going to take a look at this particular distribution. Okay, here's our normal distribution. And if it's the distribution that we're talking about here, and I'm using this to represent it, the mean is 68 inches, and the standard deviation is 4 inches. Well, this is marked off 1 standard deviation below and above, 2 above and below, and so on and so forth. So we're talking about 4 inches. So 64 to 72 inches, right? Well, 64 inches is going to be 1 standard deviation below the mean. It's going to be here. And that's 64 inches. And 72 inches is going to be 4 inches or 1 standard deviation above the mean. So this must represent 72 inches. This represents 64. And what is the area between them? 68%, right? What percentage of men what percentage of men in this population have a height less than 68 inches? How much? Okay, good. How about less than 64 inches? It's that area I just crosshatched, right? Well, that's kind of, let's think about this for a second. 50% of the population is less than 68, right? And we know that this area in here is 68%. One other property in normal distribution, it's symmetrical. So if this is 68%, what's the area in here?
It's half, it's
34%, exactly. Good work. 34%. What does that leave for this area? If this is 50% from here to the left, and this is 16%. Okay, everybody get that? Okay, that area is 16%. We can predict from this distribution that 16% of the population is going to be below 64 inches tall. Okay, did we ask for anything else there? Yes. I'm sorry, yes.
Could you do 68 minus 1 and just divide it by 2?
Absolutely. Exactly the same thing because it's symmetrical. You could say 68% is accounted for below and above, and that leaves 32%. So since it's symmetrical, that left tail and that right tail, matter of fact, now that you mentioned that, what can you say about that right tail? You can say 16% of the people in this population are above 72 inches. Okay, cool, right? We're going to use this for all sorts of things. Let's apply this again. Okay, before I move on, what's the probability of a male being between 60 and 76 inches? Okay, well, two standard deviations below was 60, and two standard deviations above was 76. So we're talking about this area in here, and that's two standard deviations. And what do we say that area was? 95%. Okay. What's the probability of a male being below 60 inches? Hang on a second. We used up 95% for this whole central area, 60 to 70, 76, right? So we only have 5% left. But we have two tails. We have males above 76 and males below 60. So 5%, that's split evenly between these two because it's symmetrical. So 2.5% of the men are above 76 inches. 2.5% of the men are below 60 inches. Okay? I don't hear a lot of agreement. Okay, we're good. Okay, we're gonna get enough examples of this that like I think it'll settle in. Okay, I'm gonna change pages here. I'm gonna give myself a fresh page, a fresh graph to work with. Now again, the shape of this thing, whether it's tall and narrow or flat and squat, if it's a normal distribution, I really don't care about the shape because I'm really concerned about standard deviations, not how really genuinely wide or narrow it is. So I'm going to use the same graph to start off with to help me work this out. Assume the heights of adult Caucasian women have a mean of 63 inches and a standard deviation of 3 inches. Okay, so we've got a similar problem here, except different numbers. 63 inches. Okay, our mean is 63 inches, and our standard deviation is 3 inches. And first question is, what percentage of women are taller than 63 inches? 50%. Good. Okay. Let's see, taller than 66 inches. Well, one standard deviation above is 66 inches, right? What percentage of the women are taller than 66 inches? Okay. Well, we know that between one standard deviation above and one standard deviation below is 68%. And since this is since this is symmetrical, this has to be 34%. Okay, that leaves how much in the upper part of that distribution? 16, right? 16%. Everybody comfortable with that? Okay, because this is 50% from here out. This is 34% is accounted for here because it's half of that 68%. So that leaves us with 16%. And last question there is less than 60 inches. Well, 60 inches is going to be, let's see, this is 60 inches. That's one standard deviation below. We've got the same situation. This also is going to be 16%. Okay? All right, let's move on to another one. And as we go through these, I think you'll probably get a bit more comfortable with them. Gestation time for humans has a mean of 266 days and a standard deviation of 25. I'll put this in here first. Okay, mean of 255 days and a standard deviation of 25 days. Can you see that? Maybe we should turn down that light in the back. Can we Levi, can we kill the light back there? Make it a little easier to see this. Okay, great. Okay, let me just make this a little bit bigger too. Okay, so standard deviation, let's see what we got here now in the way of questions about this. What percentage of pregnancies would you expect to be greater than 291 days? Mean was 256?
266.
Okay, 256. I'll take your word for it. 266. Yeah, okay. 266. Okay, 266. What percentage of the pregnancies would you expect to be greater than 291 days? Well, 291 days minus 266, not surprisingly, is 25 days, right?
Yep.
Okay. So, and I picked that day because this would be 291 days, would be one standard deviation above the mean of 266. What percentage would be longer than 291 days? Right? Well, we've done this about 9 times this time. So what's that going to be? 16%. What percentage of pregnancies would be less than 291 days or less than one standard deviation above the mean? From here all the way down. 80, bingo, 84%. Right? Because all of this represents 100% of the pregnancies. Right? Okay. So let's see what next question is. Less than 241 days. Okay, 241 plus 25 is going to be 266. So I know that's one standard deviation below the mean. 241. Okay, so that's one standard deviation below the mean. What did it ask? What percentage of pregnancy would be less than 241 days? Right? Less than one standard deviation below the mean. What's that area going to be? 16% again, right? Because this is going to be 34, this is going to be 34, this is going to be 16. Okay, less than 241 days or greater than 291. Ah, good, excellent. 36%, 32%. Okay, how did she get that 32%? Notice I said less than 241 days or greater than 291 days. That means less than this or greater than this. So I'm only interested in the area in the two tails. What percentage of pregnancy is going to be less than 241 days? What percentage are greater than 291? And since I would allow both those conditions, I'm adding the percentages together. If I had asked what percentage are between 241 and 291, it's going to be 68%. Right?
So, Tony, the ones in the two sides space, just 100 minus 68?
Exactly. Yes. Okay. Okay, good. So let me just take a quick look, see if we got any questions online. Okay. Okay, and yes, we do call this the 68, 95, 99.7 rule. Okay? To make it easy to remember. There's other descriptions that we use for it. Okay. Okay, good. Now let's take a look at the next problem. Okay, so now, let's say we want to be a bit more accurate than this, or let's say, even before we get to more accurate, there's going to be we're going to run into an issue here pretty quickly. Okay, and that issue is going to be, see if it comes up here. Okay, next problem. Assume that the heights of adult U.S. women has a mean of 63 inches and a standard deviation of 2 inches. Same problem as before, except we changed the standard deviation. Okay, what percentage of women would you expect to have a mean height less than 63 inches? Easy enough, 50%. Less than 62 inches. I got a problem there. Let me see if I can't describe what that problem is going to be that I have now. Oops. Let's see if I can't get this to go up a little. Good. Okay. So I said that the mean is 63 inches. The standard deviation is 2 inches. And okay, my mean is 63 inches. My standard deviation is 2. First question I asked is what's the probability of being less than 63 inches? And that was, of course, 50%. No problem. Okay, what's the probability that a woman is a randomly selected woman from this population? Or you could also look at it as the percentage of the population. What's the probability that they're less than 62 inches? Well, less than 62 inches. Well, one standard deviation is 2 inches, so one standard deviation would be 61 inches, right? So now we're looking for the percentage of the population that is less than 62 inches. How many standard deviations below 63 inches is 62 inches?
Say half.
A half a standard deviation, right? We're going to give that number a special name. We're going to call it the z-score. The z-score is just another way of saying the number of standard deviations away from the mean. Okay, in this case, the z-score, number of standard deviations away from the mean, is not just 1/2. It's below the mean, so I'm going to call it minus 1/2. A z-score, what value would have a z-score of plus 1/2? 64. Exactly, 64 inches, 65 inches. 64 inches would have a z-score of plus 1/2. In this case, we're looking at minus 1/2. Okay, so I want to find out what the area here is between this line, between 62 inches, and the rest of the population, the whole left side of this population. I need this area. Well, that rule that we were just using about the normal distribution, an approximation rule, isn't going to help me now. I need another way to measure this, okay? And there's a couple of ways that I can do this. The simplest way is to, since I have all these, since the standard deviation, excuse me, since the normal distribution is based on probability theory, then it doesn't seem that surprising that there would be a complicated formula that describes the shape of this curve in all these areas. Okay, we wouldn't want to apply that formula to every problem because it's very complex. But we could take advantage of that formula to make a table that represents all of these areas. So instead of using just the rule, oh, this is 68%, this is 95, we now have a table for many more areas or z-scores, standard deviations or z-scores that represent those areas. So I'm going to look that up. You have a couple that you could take off of Blackboard that I uploaded. For instance, I'm going to open a couple of them because I want to point something out about them. Okay, so now I'm going to open up this one first. This one is in a textbook that we're not actually using. Okay, however, you could use this. You could use any table you want. There's a million of these on the internet, and every statistical textbook is going to have a version of this table. This particular table shows, almost all of them are going to start off with a description on top of what area that the table is showing you. Okay, so in other words, this table is saying that the z-score that you look up on this table represents the area from that z-score down. That's exactly what we want. We want from negative 1/2 down. That's the area we're interested in this case. Okay, so I can use this table to look up that area. And the way it works is that we can look up z-scores that have 3 digits, a whole number and 2 decimal places. And the way that we do that is that we can look up like the z-score of 1.8. Here's the z-score of negative 1.8. Okay, you can see z at the top here. This whole column represents the z-score, the first 2 digits of the z-score, negative 1.6. Let's say I wanted to look up the z-score for negative 1.64. Okay, if you look at the column here, each one of these columns represents the next digit. So z-score for 1.64 would be 1.60, 1, 2, 3, 4. This would represent the area to the left of that z-score, 1.64. So what's the z-score we're interested in? 0.5, right? 0.50. Okay, so I'm going to go here to 0.5. So which column am I going to use? Well, the next digit is a 0 because it's only 1/2, right? 0.50. So it's going to be 0.3085. So what does that tell us about that area? It tells us that that area is 30.85%. Oops. I seem to have upped the wrong end. This area with a z-score equal to minus 0.50 that area that percentage of the distribution or percentage of the population or probability of picking an individual, a random individual that has a height less than 62 inches or with a z-score less than negative 0.5, that area is 0.3085, or in other words, a little less than 31%, right? 30.85%. Yes?
Sorry, I must have missed it. How did you get the z-score?
I got the z-score because we knew that the mean was 63, right? And we knew that one standard deviation below that, since the standard deviation is 2, one standard deviation below that would have been 61, right? So 62 represents half of a standard deviation below the mean. The reason why it's half is because it's half a standard deviation below. It's only one below instead of 2. And the reason why it's negative is because it's to the left of the mean. That's a negative. Had we been looking for a 64, the z-score for 64 would have been plus 0.5. Okay, now you can use a formula if you want to determine that. Z is equal to x, the value you're interested in, minus the mean over the standard deviation. Okay, if I use that formula, what's x? X is 62. The mean minus the mean is 63 over the standard deviation, which is 2. So that's just 1 over 2. Actually, minus 1 over 2. Okay, so you can do it either. You can use the formula if you want. In fact, when these numbers get a little bit more complicated than we're using right now, the formula is going to come in handy. Everybody comfortable with this so far? Okay?
Hey, Tony?
Yes.
Question. Even though we're getting that z is negative, that percentile is always going to be positive, right? We're never going to have a negative.
No, never going to be a negative percentage of probability, right? Probabilities are always between 0 and 1, and percentages are always positive numbers, okay? So now let's take a look at the next problem. Next question that we have in this problem, if I can find it ever again. Okay, what did I do with it? There we go. Okay, so how about greater than 66 inches? Let's take a look at this again. 66 inches is going to be, let's see, this is 63, add 2 to it, 65, so 66 is going to be about here. Okay, what's the z-score for 66 inches? Let's use this formula. The z-score is equal to x, 66, minus 63 over 2. What's that? 1.5, right? Plus or minus?
Plus.
Right, plus 1.5. So I'm going to go back to my table. Okay, and what did it ask for? It asked for the area greater than 66 inches. Oh, that's a little confusing now. It's asking for the area above 66 inches. Let me go back to my table and see what my table actually tells me about. My table only tells me about the area below that point, but that's okay because we know that the entire probability is equal to 1, so we're going to be able to deal with that later. Now this table, the way that this particular book presents this, all the negative areas are on one page. All the positive z-scores are in another. And you notice that it still shows the area from the z-score you're calculating to the left, the entire left side of the distribution, right? In the case of positive numbers, it's always more than half of the distribution because you're on that side of the mean. Okay, in the case of negative z-scores, it's always to the left of the mean, it's always less than 50%. In fact, the z-score of 0 is 50%. You can see the biggest number you have there is an area of 0 for 50% of the population, for z-score 0. Okay, and now let's take a look at this. Now our z-score, we're going to look up our the area to the left of a z-score of 1.5. Z-score is 1.5, and again, we're not using another decimal point, so it's 1.50, so it's this one right next to it, so 93.9332. So the area to the left of 66, or in other words, a z-score of 1.5, is 90, what was it again? 0.9332. Or in other words, you could also say 93.32%. Okay, I'm just going to call it 93. I'm just going to call it for the moment 93, right? It's the area to the left here is 93%. What does that leave for the percentage of people that are taller than 66 inches? 0.07, or if you actually calculated, it's 0.0678, something like that. 0.0668, right? Yes.
So say you lose the positive half of your chart.
Yes.
Can you just take negative 1.5 and subtract it from 1?
Yes, because it's symmetrical. In other words, if I looked for the z-score for negative 1.5, right? The z-score for negative 1.5, see what we get. Z-score for negative 1.5 is 0.0668, right? It's exactly what we calculated, the area to the left of that, right? So you can use this table in all sorts of handy ways. Okay, this is a nice table because you don't have to worry about negatives and positives and figuring it all out and keeping track. It'll always tell you the area to the left of that point. A lot of tables don't do that. Some tables will only provide, some books will only provide you with a single table. Let me see if I can find the right
So
chart.
Tony, when in doubt, just use that chart or whatever?
Yeah, I like this one the best. Okay, now, but that's not always what you're going to get. Oops, hang on a second. I know I got another one here.
That's the one we're going to get. Wait, so what's the answer to the greater
You can use anything. You can bring your own. I'm sorry.
What's the answer to the greater than 66%?
The answer was 6.68%, 0.0668, 0.0668, right? Right. 90.977, whatever it was, subtracted from 1, right? Okay, let's see. Let me see if I can't find my table here. Normal distribution. I might have to look one up online now because I can't find mine. Norm. This. Uh, how about Z table? I'll bet you I would have it underneath that. That's Agresti also. I want to find another one for you, show you how that they can be different. Tell you what, I'll go on the internet, find one. And you can bring whichever one, you can use whichever one you feel most comfortable with. Okay, let's take a look at this table right here. See if I can't get it to blow up big enough to be clear. That's not what I want. It's going to make me wait. Here we go. I'm going to actually pull that off so I can enlarge it, if it'll let me. Okay, let's take a look at this chart. This chart works similar to the one we had before, right? It shows you to the area to the left of the z-score, right? But it only shows you one page, right? It doesn't tell you about negative and positive numbers. So if you want to know the area to the left of a z-score of 1, what you have to do is you have to look up the, actually it looks like that it's only one page out of 2, right? It would show you, it would give you the area to the left of 1, which is 15.87. Would have been, remember our estimate was 16%. So you would have to use that to figure out what the area above and below 1 standard deviation above the mean would be. Let me see if I can't find a better chart to show that with. You can certainly ask a question.
Well, using the first table that we did,
Yes?
it's really counterintuitive that like we calculated the z-score being positive, and yet if we had just gone to the negative 1.5, we would have gotten the answer we were looking for.
Yeah, that's kind of odd, right?
Yeah.
because it's symmetrical. You could certainly do that if you want, but many people find that a little confusing using a single table for both the negative and the positive z-scores. See, now, if you remember that that's the case, right, you'll be able to do that without a problem. But for instance, if I had asked you what's the area below 1.5 standard deviation 1.5, and you had done that, you would have had to subtract it from 1. Catch what I'm saying?
Because it's given above it?
Right. In other words, that worked because the problem asked you for the area above a z-score of 1.5, right? If it asked you for an area below a z-score of 1.5, it would have been easier with this agresti chart.
So the z-score still would have been positive, but you would have been looking for the area below.
Exactly. In other words, the real thing that the real point of doing this is to be able to predict the probability or the area that's under this distribution. If I ask you, what's the probability here, for instance, if that problem had been, what's the probability of being of someone in this population being under 66 inches tall? If you went to the agresti chart and looked up positive 1.5, you'd have the answer instantly. But if you only had that one table, you would have had to, it would have given you, it would have, if you only had that one table, then it would, well, let's see, it would have given you a value. Actually, let me see if I can't find one. We'll try a couple of examples with both. Oh, here's another one. What does this one do?
The area to the right.
Yeah, this one gives you the area to the right, right? Well, what good is that, right? Well, again, it gives you, since this is symmetrical, it doesn't matter whether you're looking at the right side or the left side, you can still use the same table. For instance, right now, 1.5, this would be the area to the right. If we looked up the same z-score for a height of, what was it, 64 inches or something like 66 inches, that would be a z-score of 1.5. It would give you an area of 6%, 6.0668, right? But that would be the area above 66 inches tall. If you were asked what's the area, what's the percentage or the area below 66 inches tall, you'd have to subtract 1. Okay, does that make sense? In our chart, it would give you the area to the left of this instead of to the right of this. So to find the other area, you'd have to subtract from 1. Long story short, no matter what they give you, there's going to be times when you have to juggle the numbers. Does that make sense?
So you basically should like shade the area of what you're being asked.
Ah,
Whether it matches the chart or not.
exactly right. In other words, I would suggest, at least in the beginning, until you feel really comfortable with it, draw a nasty looking chart like this, scribble on it like I just did, right? Except use your own, like be a little neater, and it'll help you avoid making a mistake and finding the wrong area. Like for instance, right now, if I had asked for 66 inches or greater, right, and you went to either one of these tables and you got a number like 9773, right, 0.9773, right, would you be able to mistake that area for 97%? No, you would know immediately, I got to subtract from 1, right? In other words, if I knew I was looking for an area above this, and I went to a Z table and it gave me 97%, you would know immediately, well, that must be from this side down. So I need to subtract it from 1 to get the right answer. But if you didn't draw this, you might forget to do that and say, oh, the answer is 97%, right? That's why it's valuable that you kind of just sketch this out. I've pre-drawn this curve, right, just to make it quick and easy for us, right? But each time you do it, you could just draw your own. I mean, here, you don't need that, right? Just do this, right? And you can sketch it yourself, right? The mean, standard deviation, that whatever x is, and so on and so forth. And the z-score is going to be x minus mu over sigma is going to be a z-score, whatever that is. This is going to be the area below it. This is going to be the area above it. Okay, and you can use any table you want, right? And you can practice whatever table you wind up practicing with. Just bring that with you and print it out and bring it with you and use that. I happen to like the Agresti one because it's got the negative and positive numbers. It's a little bit quick. I find it a little bit faster and more convenient. Okay, yes.
Well, can I ask a silly question now with respect to the?
They're not, there's no silly questions, especially at this stage, since this is the first time you guys have ever seen this, yeah.
Okay. With respect to drawing, because they always say pictures worth 1,000 words.
Yep.
And you pick that, let's say the example, 0.97, 73, you would say that now you can't really go that much more above it too, right? So that's why it's everything below?
Right. Well,
Okay.
you got to, what you're doing is you're answering the question. You go in the direction the question leads you. If it asks you what's the percentage of population below this number, you go to the left. What's the percentage of population above? You go to the right. You're looking interested in the area to the right.
Maybe it was just too big or something.
No, it's you're really just answer the question. In other words, read the question, answer the actual question itself. Okay, so let's see, let's go on to another problem. Kind of warm in here, right? Always, yeah. Okay, let me get back to this document. If I can, I'll reopen it. There we go. Okay, let's do one more of these this way, and then I'm going to do it slightly different way. Body temperature of adults has a mean of 98.6 degrees Fahrenheit and a standard deviation of 0.6 degrees Fahrenheit. Find the probability that a randomly selected individual has a mean body temperature, and we'll go ahead and do it. First thing I'm going to do is draw the graph. Okay, let me see if I can't keep these together. Okay, so the mean is equal to 98 degrees, 98.6. 98.6. Standard deviation for this population was 0.6. And we're interested in the percentage of the population that has a mean temperature below 99 degrees. Okay, as 99 degrees is somewhere to the right of the mean. Okay, and what we're interested in the percentage of the population that's above that, to the right, this area in here. So what's the z-score for this? Z is equal to what? How much? What's x? 99 minus 98.6 over 0.6. What's Z equal to? 0.4 over 0.6 is equal to 0.67. Right? Positive 0.67, right? Because it's to the right, because mathematically it comes out to be positive and it's to the right of the mean. So we're looking for the area above 98.6. I'm sorry, I don't have that. Oh, yeah, I do have that. I think this is that. No. Did I close that thing? Oh, here it is. Nope. I still have it. I'm going to open this table up. See this one that we just used, right? We're looking for the area above. This is going to be really handy to use this one, isn't it? So let's see the z-score. Z-score for 0.67, 0.60, 1, 2, 3, 4, 5, 6, 7 is 25.14, 0.2514. So the area above that is 25.14, right? 0.2514. So the percentage of people in this population have a mean temperature above 99 is 25.14% of the population. Probability of picking an individual at random out of this population that has a mean body temperature above 99 is 0.2514, right? So now, if I had the other table, the Agresti table, and I went to positive 0.66, 0.6, 1, 2, 3, 4, 5, 6, 7 actually, I get 0.7454. Why do I get that? Because it's telling me the area to the left of that. Right? They give you the same answer. They're just giving you a different area of the curve. right? Except that if I ask you for the percentage of people above that, it's 2.51. If I ask you for the percentage of people below that, it's 0.7454. So does either one of these charts have a big advantage? Not really, because it depends on what the question is, right? Because in either case, if I had asked you the other direction, you would have had to subtract from one. Yes.
So I'm following what we're doing mechanically, but like, how do, what's the relationship between the Z-score and that number we're finding? Like we're calculating the Z-score and then we're like finding this other number on this chart. What is that?
That the other area, the other number is the percentage, the area of the distribution that is between that point and the entire distribution. In other words, it's the area that's represented under this curve, the percentage of it. So that for instance, z-score 0 is the mean. So 50%, half of this distribution is above the mean, and the other half is below the mean. Okay, and in this case, 25% of this distribution was above this number. So that area, the area represents, you can look at it two ways. You can look at it to represent the percentage of people that have that value or above or below, or the probability of picking an individual that has that value above or below that level. Yes?
I'm getting 7486.
7486 from
I think
which table?
the next year.
Okay, what was it again? Point 7486. No, he's got the area to the left. He knows that. I think it's because, did you use 0.66 and I used 0.67 for 2/3? Yeah, that's the only difference.
I think you use 26.
I use points. Yeah, it could be.
I just wanted to make sure.
Yeah, yeah. That's most likely. I think I'm pretty sure that's what happened. Okay, so now, and the next question is less than 98 degrees. That's actually 0.6 below. So that's actually one standard deviation below, right? Because standard deviation is 0.1. Less than or greater than 98 or 99. Oh, well, let's go ahead and do that. Okay, let me go back here. I need a bigger screen here, and make things a lot easier.
Tony,
Yes.
just quickly, less than the one standard deviation is 16%.
Yeah, let's take a look. Okay, 98 would be about here, right? And as it happens, the z-score for 98 is going to be 98 minus 98.6 over 0.6. Standard deviation is -1, right? Z-score -1 represents a temperature of 98 degrees. So we know that the area to the left of that is going to be approximately 16%. We know that from our work before with the estimations. However, we have this tool. Let's go ahead and use it. This is more precise, right? So what is the area to the left of a z-score of 1? Well, if I use this chart, it tells me the area to the right, in the right tail, but I know it's going to be symmetrical in the left tail. So what is it? It's 15.87. So this area is 0.1587 is this area in here. Okay, and let's talk about the next two parts of this question. Next two parts of this question are, what percentage of the population is less than 98 or greater than 99? In other words, in this area below 98 or in this area above 99? Well, it's the sum of 15.87% and 25.14%. Yes?
I see how you said that, but actually that was 15.7, not 16. On like a test for him, would you accept 16 as the right answer?
That's a good question. You'd have to look at it in context. Okay, so like in other words, I would say in general, most likely yes, but you might want to look at it in context. Like in other words, if we're talking about if the numbers that we give you are 98.64 or something like that, and so on and so forth, and we're giving you 3 or 4 significant digits, we probably want an answer back in that same range. No, like in other words, if I say, what's the probability of somebody being shorter than 62 inches, right? Well, that's not very precise. If I said to you, what's the probability of being less than 62.14 inches? Well, then I'd probably be looking for a more accurate percentage, right? And not only that, but anytime you do a measurement or calculation, your result is only as good as the data that you started with in terms of significant digits. In other words, if I told you that somebody's height, like somebody's height is 62 inches, and I want you to calculate their BMI, right? You wouldn't give me their BMI as 27.84 because I didn't give you their height that accurately. If I had said their height was 62.5 inches, well, then maybe you might give me their BMI as 25.7. In other words, give me the answer in basically the same number of significant digits as I gave you the input data. Make sense? If I only give it to you in 2 digits, then probably I'm going to be satisfied with 2 digits. That's probably true for most calculations that you do. In other words, I get I do a lot of work with water, and I see lab reports all the time, pH 7.973, right? Why do they put pH 7.973? Because that's what the digital meter said. The digital meter, if you look in the manual, is only good to plus or minus zero point 0.3, right? That's the range of accuracy for that meter when it's properly calibrated. To put 7.934 or whatever, put 3 decimal places after the pH, after the initial pH number, makes no sense because the instrument ain't that accurate. So you have to kind of balance this. So on a test, you can raise your hand and say, hey, how many decimal places you want it to. In real life, you got to make a real judgment. So I'm more concerned you make the real judgment in real life than on the test, right? Because on the test, we're probably going to be pretty lenient. Okay, at least with rounding numbers. Okay, but in real life, keep that in mind that if your reading is only good to 2 decimal places, don't give an answer in 4 decimal places because it's fictional, right? You don't really have the accuracy to do that. And if you're multiplying 97.49375 by 5, right? That's as accurately as you know the second number, then the whole thing is only accurate to 1 or 2 significant digits, right? So the lowest level of significance for all of the values that you're using in your calculation. That's why this is the first time I'm saying this now. But the guys from last semester heard me say this 500 times. Later on, we're going to be doing calculations that are going to be predicated on results from previous calculations. You're going to take this number, you're going to square it, you're going to add this, you're going to divide it by this, and so on and so forth. Don't round until you get to the end. Why is that? Because if I told you the number is 6.9 and you have to square that number and multiply it by something else. If you round it to 7 and then square it and multiply it, you're multiplying the error as you go along. So don't round it, use every digit available, but then at the very end, make your judgment. How many digits should I really report this as? Okay, so in any statistical calculations, do whatever you have to do because we got the tools to, we got the tools to do calculations to like 12 digits, most likely, right? Not practical, not meaningful, but it's better you keep those digits until the very end. Okay? Okay, so now this is one way for us to do this. Let's look at, yes.
One more note about that is like when Tony says significant digits, that's like the total number of digits that are not counting trailing zeros. So 500, that's one significant digit. 50,000, that's one significant digit.